Okay, so in this session we are going to look at applications of Fubini's theorem, immediate applications of Fubini's theorem. One is the polar coordinates in Rn, which you are familiar with. So, you must have seen at least this in R2 or R3 and so on. And there is something called the convolution on L1 of Rn, which depending on the time we will define and prove some results. So, let us start with polar coordinates first. So, polar coordinates is, so for any point x in Rn minus 0 in fact, you have the radius of that point or the modulus of that point times an angular coordinate which is on the unit sphere of Rn. So, that gives us two parameters, and Rn minus the point 0 can be viewed as a product space, that is the product space of 0 infinity with the unit sphere. So, we will show that on 0 infinity and unit sphere we can put certain sigma algebras and measures, so that the integral of integral over Rn minus 0 can be transferred to an integral over 0 infinity and Sn minus 1. So, that is the Sn minus 1 is the unit sphere in Rn. So, that is the aim of this lecture. Let us start. So, polar coordinates in Rn. Okay. So, you start with any point x in Rn minus 0. Okay. So, we can write x as mod x times, let us say, omega, where omega is a point in Sn minus 1. So, Sn minus 1 is the sphere in, so y in Rn, such that modulus of y equal to 1. So, this is the unit sphere in Rn, unit sphere in Rn. Okay. So, in R2 it is the unit circle, and we can identify Rn minus 0 to be the product space of 0 infinity. Well, where is the 0 infinity coming from? Mod x is a point in 0 infinity, right, cross Sn minus 1. What is the identification? X going to mod x comma some omega, right, omega in Sn minus 1. So, if you want, omega is actually x by mod x, correct, that is a point in Sn minus 1. Okay. So, we put measures on the right hand side, and then we will see that it gives us Lebesgue measure on the left hand side. Okay. So, consider two sigma finite measure spaces. One is 0 infinity, that is my space x. Then I have a sigma algebra, which is the Lebesgue sigma algebra of 0 infinity, and the measure r to the n minus 1 dr. Okay. So, I will explain what this means. So, let us call this mu. So, 0 infinity is clear, that is the space x, 0 infinity. What is the Lebesgue sigma algebra of 0 infinity? Well, we have seen this before. You can always restrict to a subset, right. So, this is the collection of all Lebesgue sets in the real line which are contained in 0 infinity, correct. You can also write this as E intersection with 0 infinity. So, you intersect with 0 infinity, where E is a arbitrary set in the Lebesgue sigma algebra of R. Okay. Both will give you the same space. Okay. So, that is one space, that is a sigma algebra. What is R minus 1 dr, r to the n minus 1 dr, that is a measure, right. So, I want to tell you how it is defined. So, if I take an set E in L0 infinity, that is the Lebesgue sigma algebra there, then mu of E is defined to be integral over E r to the n minus 1 dr. So, this is the usual Lebesgue integral, right. So, you are using this function to define the measure. So recall that exercise. If I have a positive measurable function, I can define on some measure space, right. So, I can define nu of E to be integral over E f d mu, right. Mu is the original measure, then nu is a measure, right. So, nu is a measure, it's a countably additive measure. So, that is the measure we have defined here, okay, all right. So, that is one space. The other space is Sn minus 1 and I have a sigma algebra G and I have a measure sigma. So, I should tell you what these are, right. So, if E is a subset of Sn minus 1, okay, you look at, consider E tilde, okay. So, what is E tilde? So, E tilde is S times omega, where S is between 0 and 1, okay, and omega belongs to E. Okay, so, this is a sector defined by E. Okay, so let me explain this a little bit more. So, let us look at some examples, so that will be very clear. So, I look at the unit circle in R2, that is my S1, right, Sn minus 1. So, in this case it is S1. Then I take some set E. So, let us take an arc E, okay. So, this is my arc E. That is a set in Sn minus 1, right. Then what is E tilde? So, E tilde will be you join these two endpoints to the origin. Origin is not included because S is not 0, S cannot be 0. So, whatever is inside, correct. So, whatever is inside, so let us, okay, this portion is E tilde. That is a subset of Rn, right. In this case it is a subset of R2. So, this is a subset of Rn, okay, that is the sector defined by that particular arc. So, E can be an arbitrary subset of the unit sphere, okay. Now, I want to define G, right. So, the script G, the sigma algebra of subsets of Sn minus 1. So, this is all those sets E in Sn minus 1 such that E tilde is a Lebesgue set in L of Rn, okay. So, if I look at the sector and if I get a Lebesgue set, then the boundary that is inside the sigma algebra we want to consider. So, notice that the Borel sigma algebra of Sn minus 1 is contained in G. Well, what does that mean? Sn minus 1 first of all is a metric space, right. Sn minus 1 is contained in Rn and so is a metric space, right. We have the usual distance on Sn minus 1 which is coming from the distance on Rn, usual metric. So, any metric space has a Borel sigma algebra, right. So, B of Sn minus 1 is the sigma algebra generated by open sets in. So, open makes sense because it is a metric space, right. So, open sets in Sn minus 1. So, you take any open set in Sn minus 1, that will be in the Borel sigma algebra and generate the sigma algebra, you will get the Borel sigma algebra. So, to show this, what do you need to show? You need to show that open sets are inside G, right. But that is trivial, right. If E is open, so that means it would be an arc like this or some other open set, the sector will be open, okay. So, that follows. So, this follows from E open, E contained in Sn minus 1 open implies E tilde which is a subset of Rn minus 0, that is open. So, any open set E gives me E tilde which is an open set and so it will be in the Lebesgue sigma algebra, which means that any open set is in G. So, the Borel sigma algebra itself will be in G, okay. So, you have to check that G is a sigma algebra first. Check that this definition makes G a sigma algebra. Okay. And so if open sets are contained in G, since G is a sigma algebra generated by the open sets will also be in G. Okay, so we are fine. So we have the space Sn minus 1, we have the sigma algebra G, but we haven't defined the measure. Okay, so what is the measure? So for E in G, sigma of E, so small sigma is the measure, right? So I am denoting it by small sigma. Sigma of E is, well, you go to E tilde. So E tilde is this sector, and E is in G will imply E tilde is a Lebesgue set, right? So measure of that makes sense. This is the n dimensional. So M of E tilde is the n dimensional Lebesgue measure of E tilde, right? E tilde is a subset of Rn. Okay, and you multiply this with n. N is the dimension. Okay, so that's a constant. So n is the dimension. It's a constant. Okay. Okay, if you compute it in R2, you will see why sigma is defined like that. So we have now two spaces, right? So let me write it again. I have 0 infinity as space. I have the Lebesgue sigma algebra on 0 infinity. I have the measure r to the n minus 1 dr. Remember how it is defined. So this is one space, and I have the space Sn minus 1. I have the sigma algebra G. So a set is in G if its sector is a Lebesgue set, and I have the measure sigma, which is sigma. So sigma of E is n times sigma of E tilde, right? E tilde is the sector defined by E. So you can check that both are, so check that both spaces are sigma finite measure spaces. Sigma finite measure spaces. Okay, so you have to check that sigma is a measure. That is because okay, so I made a mistake here. So let me write it again. So this is n times measure, Lebesgue measure of E tilde, right? Since capital M is a measure, small m is a measure, sigma is also a measure. Okay, so because if EJs are disjoint here, then EJ tildes will be disjoint, right? The sectors will have to be disjoint. So again, look at some picture. So if this is E1 and this is E2, they are disjoint, the sectors are also disjoint, right? So this portion and this portion are disjoint. So disjoint sets will go to disjoint sets in the sector, and so it will add up. So that is why it is a measure. So that part is easy. Check that both are sigma finite. In fact, a sigma of Sn minus 1 is a finite quantity. So it's a finite measure, but this is a infinite measure, but it is sigma finite. So theorem, let f be a measurable function on Rn, then so if the integrals exist, okay, so that part I will not bother. You can take a positive function, or f is in L1. So maybe let's put the assumption clearly. Let f belongs to L1 of Rn. Okay, then integral over Rn, well, Rn minus 0 strictly speaking, but integral over Rn and integral over Rn minus 0 are same, right? Because 0, the point has measure 0. F dm, this I want to write as integral over 0 infinity, integral over Sn minus 1. Okay, so I am taking the product of this and this, right? Sn minus 1, f of, so x is written as the product of two things. So it is r omega, and on Sn minus 1 my measure is sigma. So d sigma omega. Okay, so omega is the integral first, and I have the measure r to the n minus 1 dr. That is this measure, right? So this is the claim. So this is called polar coordinates. polar coordinates. So you must have seen this several times in the case of R2, R3 and so on. It is true in general. So there are several things which are implicit in this, which I will not bother to explain because you have seen this several times now. To write the inner integral, this has to be measurable and so on, and the integral will be finite for almost all R, etc., etc. So such things, whatever we saw in Fubini's theorem will be applicable here. Okay, so we will just prove the identity in general. That is all we will do. Okay, all the other justifications are done as in Fubini's theorem. So proof. Okay. Okay, so keep the identity in mind. So first so I have two spaces. So so the notation becomes a bit ugly. So you keep track of the sets we are writing. So this I have a sigma algebra. So this is L of 0 infinity, and I have R to the n minus 1 dr. Okay, and I have Sn minus 1. I have G and sigma. Okay, so that we will keep. So first, so as all these proofs, any theorem like this, since f is in L1, what we do is we prove this result for f equal to chi e, where E is a Lebesgue set. Okay, and then so that will imply for simple functions. Okay, which will imply for positive functions by MCT, etc. Right? You can complete it for all functions by taking real functions and then taking linear, etc., etc. So that part I leave it to you. So we just need to show it for an arbitrary set. Okay. So first we will take, so I need to look at sets which are inside L of 0 infinity, right? L of Rn minus 0, strictly speaking, because we will not include 0. So first take E1. So let E1 to be equal to open interval 0 1, and E2 any set inside G. So there we are taking a arbitrary set in G. Okay, but here we are taking the interval 0 1. So that is very specific. So what is E1 cross E2? E1 cross E2 can be identified with, well, this is the set SW, right, where 0 less than S less than 1 and W is in E2. And this is simply the definition of E2 tilde. Correct? Alright. So now let us look at the product measure. So we call this mu. Okay, so that I don't have to keep writing R to the n minus 1 dr. So you look at mu cross sigma. So mu cross sigma makes sense, right? I have two sigma finite measure spaces. I know the product makes sense. So 0 infinity cross Sn minus 1, that is my Rn minus 1. I have L of 0 infinity cross G, and I also have mu cross sigma, right? Okay, so mu cross sigma of E1 cross E2. Well, this is a measurable rectangle. So the measure just is the product, right? So that is mu of E1 into sigma of E2. Sigma of E2. Correct? Well, which by definition is, what is mu of E1? Mu of E1 is integral over E1 R to the n minus 1 dr times sigma of E2 is n times measure of E2 tilde. Right? That is the definition. But E1 is 0 1. So what is this? So this is integral 0 to 1 R to the n minus 1 dr, which is 1 by n. So this is equal to 1 by n, and I have n here, so that gets cancelled. So this is equal to m of E2 tilde. So what we just proved was E1 in the cross E2 identified with E2 tilde, and we have mu cross sigma of E1 cross E2 equal to m of E2 tilde. So on E1 cross E2 these measures agree, right, that is what we want to say. But E1 is a specific set 0 1. Okay. So now change E1 to 0b, where b is a positive number, and let us do the same thing again. Okay. So I have E1 equal to some set 0b, where b is some positive number. E2 is still a general set inside Sn minus 1, but it belongs to the sigma algebra G, right. Then how would E1 cross E2 look like? Okay. So let us try to understand this. So this is my unit circle. Let us say this is E2, okay, and b is some number, right. So E1 cross E2 is identified with all those SW where 0 is less than S less than B. So instead of 1 now go till B, and W is in of course E2. Well, how does it look like? Well, if B is greater than 1, so you will have a sector like this, correct. So this distance is B. This distance is B. Okay. Well, which is nothing but the dilation of this portion. So you look at this portion, which is E2 tilde, right, and you multiply it with B, right. So this is nothing but B times E2 tilde, the dilation, right. So remember dilation. Okay. So now let us compute the measures again. So mu cross sigma of this measurable rectangle E1 cross E2, where E1 is 0b. Okay. This is nothing but, well, I have this to be equal to mu of E1 into sigma of E2 by definition. Okay. So mu of E1 now would be integral 0 to b r to the n minus 1 dr, right, because E1 is 0 to the b, and mu is defined by r to the n minus 1 dr, times sigma of E2 is of course n times measure of E2 tilde. Okay. Well, what is this? Here this will give me b to the n by n. So by n and into n will get cancelled. So I will have b to the n times measure of E2 tilde. But remember the dilation invariance properties of Lebesgue measure on Rn. So this is E2 tilde times b, and you look at the measure of that. So notice that E1 cross E2 is identified with this, and we are saying this measure and this measure equal on those sets. So on measurable rectangles of this form E1 cross E2, they agree. So now you can take limits. So mu cross sigma and m, which is the Lebesgue measure on n dimensional space, n dimensional Lebesgue measure, okay, agree on 0b cross E2, right, for every b positive and for every E2 inside Sn minus 1, which is a measurable set. Okay, so that tells me, so now I can take limits. So take limits. So this will be, from here onwards I will be somewhat brief in telling you what exactly needs to be done, because it is all limiting properties. Okay. So limiting arguments will give the same to be true on sets of the form 0a closed cross E2, right. A is positive and E2 is in G. Well, how do you do that? You write open 0 closed at A to be intersection of open 0 A plus 1 by n open. And so when I take product with E2, I will be taking product with each of them, and then so what I want to say is the sequence of set 0 A plus 1 by n decreases to 0 A closed, and use limiting, right. So because on these sets cross E2 we know they agree. So on the limiting sets also they will agree. Now from 0 A and open interval 0 B you can go to all open intervals, right, by subtraction. Well, if you subtract, for example, if 0 is here, A is here and B is here, you subtract 0 B and 0 A, you will get AB, right, AB. So you can go to all open intervals. So the measures mu cross sigma and M will agree on sets of the type open interval AB cross E2, where E2 is a general set in G, right. So we didn't bother too much about E2. Okay. So from open intervals you can go to all Lebesgue sets, right. Go to all Lebesgue sets. So this we have seen from open sets going to Lebesgue sets. So apply the same argument. So the measure M is identified with mu cross sigma on measurable rectangles, correct, because from AB you can go to, so from here we are going to E1 cross E2, where E1 is a general Lebesgue set in 0 infinity and E2 was some general set in G. So those are the measurable rectangles, right. So these two measures agree on measurable rectangles, okay. So this would imply they agree on disjoint union of measurable rectangles, because they are measures, so they add up, okay. And then going from disjoint union of measurable rectangles to everything is by taking appropriate limits, right. So this by MCT will agree on all sets in L of 0 infinity cross G, right, in that Lebesgue sigma, in that sigma algebra, in the product sigma algebra. So this is what is polar coordinates for. Okay, so this is the part I will leave it to you. Coordinates for indicator functions. Alright. So once it is done for indicator function, this will imply polar coordinates for positive functions by MCT and simple functions, etc. Right. So that's standard argument. I will not bother about explaining this. And then from positive functions you can go to general functions, polar coordinates for general functions. Okay. So we finish with this. The point I have not explained is that the measures agreeing is same as polar coordinates for chi. So that is something I will leave it to you. You write it down. What does it mean to say that M and mu cross sigma agree on a set, right? So I mean this was the starting of Fubini's theorem, if you like. So if I know M of E is same as mu cross sigma of E, where E was a Lebesgue set in Rn minus 0. So 0 is not needed there. Then if you write down the right hand side, this is actually polar coordinates for, or whatever the theorem said, the integral polar coordinates for chi E. And once it is true for chi E, you can go to simple functions, positive functions, and then general functions in the usual manner. Okay, so we will stop here. So we have just seen one application of the Fubini's theorem, which is the polar coordinates on Rn, which you are familiar with. There are lots of other applications, so we will see at least one more in the next lecture before we go on to new topics in measure theory, especially complex measures and so on. Okay.